Hello everyone. In this section, we will talk about what is classification. Machine learning has three types: supervised learning, unsupervised learning, and reinforcement learning. While on the supervised learning, we have two classes of problem that we will deal with. One is regression problem, and the other is classification problem. We have introduced regression in the last chapter. In this chapter, we will introduce what is classification and how to deal with it. Classification is a process of categorizing a given set of data into classes. It can be performed on both structured or unstructured data. The process starts with predicting the class of given data points. The classes are often referred to as target, label, or categories. The classification predictive modeling is the task of approximating the mapping function from input variables to discrete output variables. The main goal is to identify which class or category the new data will fall into. The naive Bayes classifier is extremely faster in nature compared to other classifiers. The common use cases of classification include disease prediction, document classification, spam filter, and sentiment analysis. Let's try to understand this with a simple example. Tumor benign or malignant prediction can be identified as a classification problem. This is a binary classification, since there can be only two classes, benign or malignant. The classifier, in this case, needs training data to understand how the given input variables are related to the classes. And once the classifier is trained accurately, it can be used to predict whether the tumor is malignant or not. Since classification is a type of supervised learning, even the targets are also provided with the input data. There is a lot of classification algorithms available now, but it is not possible to conclude which one is superior to other. It depends on the application and the nature of available dataset. Let us take a look at those classification algorithms in machine learning. The most common classification algorithms are logistic regression, naive Bayes classifier, support vector machine, and artificial neural networks, etc. We have introduced logistic regression in last chapter. Now, let's discuss naive Bayes classifier, support vector machine, and artificial neural networks. Naive Bayes is a probabilistic classifier in machine learning, which is built on the principle of Bayes' theorem. Naive Bayes classifier makes an assumption that one particular feature in a class is unrelated to any other feature, and that is why it is known as naive. This picture denotes the Bayes theorem. The classification is conducted by deriving the maximum posterior, which is the maximal probability of Ci if X, with the above assumption applying to Bayes' theorem. This assumption greatly reduces the computational cost by only counting the class distribution. Even if the features depend on each other, all of these properties contribute to probability independently, and naive Bayes has able to perform impressively. Naive Bayes model is easy to make and is particularly used for comparatively large data sets. Even with a simplistic approach, Naive Bayes is known to outperform most of the classification methods in machine learning. The naive Bayes classifier requires a small amount of training data to estimate the necessary parameters to get the results. They are extremely fast in nature compared to other classifiers. The only disadvantage is that they are known to be a bad estimator. The support vector machine is a classifier that represents the training data as points in space, separated into categories by a gap as wide as possible. New points are then added to space by predicting which category they fall into and which space they will belong to. Artificial neural network is a set of connected input-output units where each connection has a weight associated with it. During the learning phase, the network learns by adjusting the weights so as to be able to predict the correct class label of the input tuples. There are many network architectures available now, like feed-forward neural network, convolutional neural network, recurrent neural network, etc. The appropriate architecture depends on the application of the model. For most cases, feed-forward models give reasonably accurate results, and for image processing applications, convolutional networks perform better. Weightings are applied to the signals passing from one layer to the other, and these are the weightings that are tuned in the training phase to adapt a neural network. We will discuss artificial neural network in details in Chapter 5. The most important part after the completion of any classifier is the evaluation to check its accuracy and efficiency. There are a lot of ways in which we can evaluate a classifier. Let us take a look at these methods listed below. Holdout method. This is the most common method to evaluate a classifier. In this method, the given dataset is divided into two parts as a test set and a train set, such as 20% and 80% respectively. The train set is used to train the data, and the unseen test set is used to test its predictive power. Cross-validation. Overfitting is the most common problem prevalent in most of the machine learning. K-fold cross-validation can be conducted to verify if the model is overfitted at all. Precision and recall. Precision is the fraction of relevant instances among the retrieved instances, while recall is the fraction of relevant instances that have been retrieved over the total amount of relevant instances. Precision and recall are used as a measurement of the relevance. ROC curve. ROC curve is used for visual comparison of classification models, which shows the relationship between the true positive rate and the false positive rate. The area under the ROC curve is the measure of the accuracy of the model. This is the end of this section. Thanks for watching and welcome to the next period.